we just want to share you. We are left over with the unit 2, right? Just a minute. We started with this, right? Yeah, we just started with the band theory of solids in the last class. In the last class, we just discussed about the what is actually free electron theory. So here, the free electron theory is also known as classical free electron theory, which is proposed by Drude and Lawrence, and which is a macroscopic theory in which they consider that the electrons are moving very freely in the given lattice points. And which is obeying the classical mechanics. See, when we deal with classical mechanics, we are talking about the macroscopic nature of the theory, right? So we are having some different types of theories also. We can just go for the microscopic theory also, which is proposed by Sommerfeld. So that is also known as quantum free electron theory. The later section will just do that. So in the present one, what we have completed in the last class is the important postulates of the classical free electron theory. So we just have very quick review of what we have completed. We are so the atoms which are the solids are composed of the closed packed atoms. You already know solid is nothing but the atoms which are arranged in a are arranged very close to each other. So and definitely the atom is possessing at the center the nucleus, and the electrons revolve around the nucleus. Now this was the assumption, basic concept of the what you can say about the atom. So the electrons are moving freely in all the positive possible directions when we consider the case of the metal, right? This theory says that the electrons are moving freely in all the possible directions, right? So in the case of metals, right? So this was the assumption which is made by Drude and Lawrence. So what is happening if you apply the electric field? What is happening to the metal if you don't apply any external field or electric field? So what is happening? So in the if you don't apply any electric field, the electrons move in random directions, and definitely they will collide with each other, and also they try to collide with the positive ions, right? So here they assume that the collision between the electrons are neglected, right? This was the assumption which is made by Drude and Lawrence. So, man, definitely they will try to attract the positive ions. So, at a particular point, and all these collisions with respect to the positive ions, there will be no loss of energy. This was the assumption which is made by the. See, whenever you are going for any collision, probably you definitely will have some loss of energy. So, what they believe, Drude and Lawrence, that when the electron and positive ion core is interacting with each other, there will be no loss of energy, right? So what is happening? This is the case when there is no electric field. So what will happen when the external electric field is applied to the free electrons in the metal? They will try to drift. They will definitely try to drift towards the positive potential, right? Now this was the case when the external field is applied. Now since the electrons here, as we said, that they are freely moving, so you can just resemble this particular aspect of free movement of electron with the free movement of molecules inside the gas. So if this is the case, then definitely should obey the movement of free electrons should obey the classical kinetic theory of the gases. So here, if this is the case, then definitely electron, as they are moving freely inside the metal, they should obey the Maxwell-Boltzmann statistics, which say that definitely as the electron is moving, definitely they possess the velocity, and that velocity can be calculated by means of the Boltzmann statistic, Maxwell-Boltzmann statistics, right? So with these assumptions, right, there are different merits and demerits of the classical free electron theory. So we just discussed first of all the merits. In the last class, we just discussed that by means of this theory, we can just verify the Ohm's law, and also we can explain the optical properties of the metals and so on, right? We are trying to just concise ourselves to one or two merits, and also in the drawbacks. This theory is, first of all, when you talk about atom and the particles which are residing, elementary particles which are residing in the atom, definitely it should be a study of microscopic study. But this theory is a macroscopic theory, and which is one of the drawbacks of classical free electron theory. And definitely with this assumption, we have another important processes or the phenomena which cannot be explained, that is ferromagnetism, superconductivity, photoelectric effect, and the Compton effect. So with this, we had discussion on this in the last class, right? So with this few words, what you can say, previous class revision, we just move to the chronic and penny. So this also we just started with. So since we just started with the chronic penny model, so what is this chronic penny model? Here, the first assumption which is made by the Drude and Lawrence, classical electron theory. So again, there are two scientists who had made their own um, consideration, and they proved whatever they have considered by means of by taking the help of some mathematical calculations. Right? We just deal with the mathematical calculation, and they say that how the electron is behaving inside the metal. So according to them, so first of all, we say that periodic potential. So periodic at regular intervals, you will find that the movement of the electrons are moving in the form of a square wells. You can just see the schematic figure. See, you can just see the schematic figure. So, and in order to explain this particular movement of the electron, they have since see when we talk about the electron here, so we are talking about that the electron is moving in the form of a wave. So when the electron is moving in the form of a wave, we need to just correlate that particular aspect with the mathematical equation. So that is what the Kronig and Penny has done. So they consider the Schrodinger wave equation. See, Schrodinger wave equation is for the particles which are behaving as a wave. So here they have taken the uh, aspect of Schrodinger wave equation. So that Schrodinger wave equation is given by dou square psi by dou x square plus 8 pi square n by h bar square in h square into e minus b into psi is equal to 0. Now this was the first equation, right? So we just discussed in the third unit what is actually the meaning of Schrodinger wave equation and what is the significance of the Schrodinger wave equation, right? So that particular aspect we just discuss in the later unit. So here you can just consider that in order to prove this chronic and penny, the movement of the electron, how the behavior of the electron inside the crystal. So that particular aspect is given by the Chronic and Penny by taking the help of Schrodinger equation. I will show you that equation also. So definitely, since it is a second order differential equation, so every second order differential equation, when you don't know the exact solution, we need to consider the solution. And this solution was given by the scientist Bloch. He says that psi of x is equal to uk of x. You can just see psi of x is equal to uk of x exponential of ikx. Now, this particular assumption, which is made by the Bloch, that the since the Schrodinger wave equation may have this type of solution. Here, when I say psi is the wave function. The wave character, wave function is mathematically resembled by a parameter called psi. I will tell you what is actually the psi is also related when we just discuss the unit 3, right? So in that you'll definitely get the a clear idea about this wave function. What is actually this wave function? For now, you can just remember that it is a mathematical representation of the wave, right? So psi of x is equal to uk of x into exponential of ikx, where k here you can just see that k is a wave vector. You already know that k is a wave vector which will define the character of the wave, right? So mu k of x, uk of x. What is this uk of x? Well, so Bloch says that uk of x can also be written as uk of x plus a. Here x means, right, we are trying to deal with as one direction. So one direction, single direction. Therefore, we have just taken the variable as x here. So uk of x into exponential of ikx. He says that Bloch says that uk of x is actually equal to uk of x plus a, which is nothing but the Bloch function, where a is nothing but the lattice constant of the crystal, right? The lattice constant, which define the dimension, which in the crystal in one dimension, right? So here the simplified, see, when we just solve this particular solution, that is equation number 2, you'll get an this particular type of equation, that is cos k is equal to p sine alpha a by alpha a plus cos alpha a. Now this particular equation number 3 we'll get after going for very what you can trivial manipulations, mathematical calculations. So here, since you are studying about physics, so we just taken the help of the equation what we get by mathematical operations. So by different mathematical operations, applying of mathematical operation, we'll get this particular function, that is cos k is equal to p sine alpha a by alpha a plus cos alpha a. So what is this value of p? We just discussed that, that is p 4 pi square ma v naught omega by h square, and alpha is equal to pi by h into 2 to me. So what is E here? Energy of the permissible values, which are, or what are the permissible values of this electron which is behaving as a wave? So with respect to equation 3, you can see that cos and sine is there. So what is the maximum minimum value of cos and sine? As you know that that is given by -1 to +1. That is a minimum and the maximum value of sine and cosine, right? So this is this particular thing you already know from your mathematics. The so as V naught as the potential, and this will definitely, what is V naught here? The potential which is existing, right, in the form of you can just say square wells are there. So where you'll find that there will be a potential with respect to the with respect to the movement of the electron towards the positive ion core. So now, as you, what is W or omega? You can say that is the width of the square well is nothing but, we can just talk in the language of what you can say, Chronic and Perry. They say that is the width of the potential barrier. So or we say that the width of the barrier, as W, as V naught is increasing, W will decrease, and the combination of this V naught omega or W will be remaining constant. And P is what? Scattering power of the potential barrier. So here, in the case, what are the important conclusions which are made by the Chronic and Perry? See, in the previous topic also, we when we discuss about the Drude and Lawrence, right? Clear, you should be very much clear. When we consider Drude and Lawrence, there are different conclusions or postulates which are made by Drude and Lawrence. In the same manner, the Chronic and Penny has given their own view about the movement of the electron in the metal, right? So what they say, that we just see for each and every point, or 1 or 2 point, you'll have the schematic diagram adjacent to that. You can, for your understanding purpose. So what they given, the movement of the electron in a periodic lattice. So why say why I'm saying periodic lattice. So periodic means what we they assume that in the crystal, since the atoms and molecules are arranged in a sequential order. So in that way, that we are taking consideration into the arrangement of the atoms are in the sequential order. So periodic at time to time, right? The movement of the electrons in a periodic lattice is characterized by, there are allowed energy bands and they separated by forbidden region. What is the meaning of allowed energy band and what is a forbidden region? So where the electron is traveling, we just say that is called allowed energy band. So electron will have some amount of energy. You can just see this. The electron is having some amount of energy. Here, as it is reaching the positive ion core, here there is a positive ion. You can just see, we have just seen the schematic diagram of the square wells, right? These are nothing but the form of square wells, or we just say that this is called allowed energy bands. And the empty space in between them, that we say that is called forbidden regions. Forbidden regions where the electron is not possessing the energy, or you can just say minimum energy possessed by the electron as it is going towards the positive ion core. So the movement of the electron, which has been explained by the Chronic and Penny, the motion of the electron in periodic lattice is characterized by the allowed energy bands and separated by a forbidden region. So you can see that on the x-axis we have taken the angle, that is alpha a. On the y-axis we have taken p sine alpha a by alpha a plus cos alpha a from the equation number 3. In the previous equation, right, we had the third equation. That third equation, an angle is taken on the x-axis, and whatever the thing which is remaining on the RHS we have taken on the y-axis. You can see, and the values, see, you can see the values which of cos and sine is given by +1 to -1 to +1. So now you can just see this is actually forbidden region, empty space, and here they are the called as the allowed energy band. So as the what is happening if I increase the angle? So what the Kronecker Penny says that as the value of alpha is increases, the width of the allowed energy band is also increasing. If you increase this value alpha a, so the width of the energy band is also increasing, and the width of the forbidden gap. So you can just see that starting from here, as I increase the value of alpha, slowly the width of, you can just see the width of the band is increasing. You see here it is increasing in the case of -1, and this is here also you can just see the here the band is the width of the band is less. Here we can see that it has been expanded, and now here when compared with this it is also more, it is increasing, right? You will see the schematic diagram for your reference if you don't understand this. So now if the potential barrier strength is very large, then the function described by the right hand side, so the function, see what is the function on the right hand side? P sine alpha by alpha plus cos alpha. So if the strength of the value of P is increasing, so what will happen? So that if you increase the barrier strength um, to the limit, more than the limit, so definitely the waveform, see the waveform will be traveling outside the what you can say the prescribed values of +1 to -1. Thus you can just say that the allowed energy band becomes narrower and the forbidden band becomes wider. Now for this is the case, this, see, 2 and 3 are completely opposite to each other. When you increase the strength of the barrier, definitely the allowed energy band will be decreasing and the width will be increasing. So what will happen if you increase more potential barrier strength? So if it is reaching, see, already we have reached to the maximum extent. Here if it is made to infinity, the allowed band reduces to a single energy. You can see the allowed energy band now has been reduced to the single energy level, right? And so this is actually when comparison with the discrete energy level of the isolated atom. So since the isolated atom will have a single atom will have an energy level, if you consider the case of a hydrogen atom, so it definitely will have a single isolated atom. It will have an energy level, right? A single energy level. So now you can see this is the level which is corresponding when P tends to infinity. Now see, this was the assumption. See why we are increasing P. See, barrier will have some amount of strength, right? So if we increase the strength, what is the effect? We can just see the in the what you can say the right hand side equation, right? Mathematically, we are just comparing it with the LHS and the RHS. If we increase further, if it's tending to infinity, what is the effect on the allowed energy bands and the forbidden energy? That we want to, that the chronic and we want to see that, and they said that this is happening. So and how this is happening, we will just show you. So when P is tending to 0, there will no energy level. See, if we have increased the P to infinity, and then we are reducing the P to minimum level, that is P tends to 0, what will happen? The particle is completely free here. So if there is no strength, if the strength is minimized, definitely electron will can move anywhere inside the metal. So what you can say from this assumptions, you can just say that if you increase the value from 0 to infinity, from free energy as it is reaching to the infinity value, when the electron is free, when the strength of the potential barrier is 0, right? So when it is reaching to the if the strength of the potential barrier is uh, is reaching to infinity, definitely the free electron is becoming a complete bounded electron. So we can just see that if you change the value of P from 0 to infinity, the what you can say the free movement of the electron is curved, and that electron now will be isolated. Okay, now we can just see, we can just, I will show you with the equations. What was the equation actually? That equation was K, mathematical way I show you, cos k a is equal to p sin alpha a, right? Plus, right? I'll just clear this. The see here, we just discussed this one, right? Now, so what I'm trying to tell is that what will happen when we just see it p tends to 0 in the later section, see p sin alpha a. Okay, I will just show this in the later part. I will just show you what is happening p tends to 0 when we are just substituting it in the equation number 3. So right, so uh, we'll move to the next one. It's very very important. So here we just now talked about the single atom, right? So when we talk about hydrogen atom, what will be the energy level? Just now we just considered, right? The energy level will be E. So as you move for a single atom to the two atoms, let us see. We are for our understanding level. I'm just talking about that. Say the single atom is hydrogen, and this two atom is helium, right? And this is a three atom beryllium, and so on. So when the atoms are increasing, definitely the energy levels will also increase. You get to see, and as the n number of atoms are there, definitely you'll have n energy level, and you cannot differentiate these energy levels. Now these energy levels, as they are very close to each other, I can see that the atoms are very close to each other, the energy levels are very much close to each other, and they will form a band. So what is the definition of solid? Everybody know that closely packed atoms. When the atoms are closely packed, the energy levels will also be closely packed, and they will form a band, right? So that is called energy band of solid. In order to understand very clearly this energy band which is existing inside the solid, we just taken a look of this, right? We just take an example, right? So energy band structure of a solid determines. So why we are studying about this energy band structure? So we need to determine whether the given solid is acting as a conductor, insulator, or a semiconductor. See, our purpose now that is that we just discuss about what is internally happening inside the solid, and what is the structure of the solid with different properties. We just discuss different diffraction methods. We discuss now. We want to compare that how the solid is behaving. Or what is that solid is known as? Either it is a metal or semi-metal or an insulator, conductor, semiconductor, or an insulator. So how we will come to know? By considering the energy band structure of the solid. So in order to understand that, so let us consider a solid is consisting. You already know, right? Solid is consisting of or contains numerous number of atoms which are closely packed. So each atom, when isolated, when I definitely, as just now we discussed, when it's isolated, definitely you'll have a single energy level. If there are two atoms, two energy levels. If there are n number of atoms, see, if we imagine all the n number of atoms of the solid to be isolated from one another, they would have completely coinciding. So if you consider also if the n atoms are not close to each other, definitely the energy levels will try to collide with each other. So in order to explain this, how this is possible, so in order to explain this particular aspect very clearly, let us consider the energy levels of an isolated atom as they are very brought closer to each other. So what will happen? They form a solid, right? So the valency, how which electrons will come when we consider the solid, right? You consider the inside the solid, you'll have an atom, sir. So each element will have some valency electrons. You already know, right? Valency electrons, they will try to interact with the adjacent neighboring atom. Hence, the valence electron constitute a single. See, bond will be formed between valence electron. You already know valence electrons are the electrons which are present in the outermost shell. And so we just say that is called valence electrons, right? So if there are n electrons, now they will have a different energy levels. Now, so we can just say we just take an example of the sodium neutral atom. You can just see we have taken the example of sodium atom. So definitely they will each atom will have a particular energy level. You can just see this. So the energy levels of sodium become bands. I just told you, since they are atoms are closely proximity of the atoms are very close to each other, they will form a band. When the atoms are close together, you can just see that the distance r naught. So the r naught is nothing but a distance. The center of the two adjacent atoms, the distance between them is said to be r naught is a distance between the two atoms in the between the atoms in the solid sodium. So we talk about sodium in the form of solid, right? Definitely, we are talking about solid. So when the atoms are in solid, they interact with each other, and the electrons have slightly different energy. You can see when you talk about a filled, complete filled state, 1s2, then this is slightly, you'll find that this is also completely filled to s2, and here you'll find that there will be 2p and so on up to 3s. So we just taken, you can just have more examples, but what we are trying to do here is that we're just taking 2 to 3 different electronic configuration values. So what will happen here? So in the energy band, allowed energy bands are continuous. So what you can just see these regions are called see in the energy band, allowed energy bands are almost continuous. So the energy band generally separated by regions. We have seen that in chronic penny also they are separated by some regions, and that regions you will not find any energy levels, and these regions are called forbidden energy gaps. So the amount of splitting at the different levels will be different. So here, when there are n atoms in the solid, there will be n quantum states in each band. And here, now the band which is formed by the atomic energy levels containing valence electrons. The band, the energy levels will try to come closer to each other, and they'll form a band. So if the valence, if the atoms, we are talking about the valence electrons, right? Inside the atoms, you'll have an electrons, right? Which are revolving around the nucleus. So when you talk about the valence electrons of the given element, so the band which is formed by this valence electron is said to be valence band. Very clear. So these electrons will have the highest energy, and above the valence band, there is a band. You definitely above the valence band, you will have a band called conduction band, and the distance between this valence band and the conduction band will be considered to be the forbidden gap. So with this, we can just say that, see, sir, you just read out this theory. We'll just see a video also for your reference, right? Just a minute. No. Right.
Physics. We know that matter keeps converting its state and gives rise to various different properties that we see around us. This story of matter is completely governed by the energies that keep stabilizing and destabilizing the matter, and depends quite a lot on the surroundings. When atoms come together to form a compound, their atomic orbital energies mix together to form molecular orbital energies. The electronic band structure of a matter describes the range of energies that an electron within the matter may have, and ranges of energy that it may not have. Now, let's take a dip into the band theory to understand it further. The electrons of a single isolated atom occupy atomic orbitals. Each orbital forms a discrete energy level. When multiple atoms join together to form into a molecule, their atomic orbitals combine to form molecular orbitals, each of which forms at a discrete energy level. As more atoms are brought together, the molecular orbitals extend larger and larger, and the energy levels of the molecule will become increasingly dense. Eventually, the collection of atoms form a giant molecule, or in other words, a solid. Types of energy bands. Let's take a look at various types of energy bands. The first one is valence band. It is the band of energy where all the valence electrons reside and are involved in the highest energy molecular orbital. And the second one is conduction band. It is a delocalized band of energy levels in a crystalline solid which is partly filled with electrons. These have some great mobility and are responsible for electrical conductivity. Fermi level energy. This level refers to the highest occupied molecular orbital at absolute zero. It is usually found at the center between the valence and conduction bands. The particles in that state have their own quantum states and generally do not interact with each other. When the temperature begins to rise above absolute zero, these particles will start moving upwards and the states below the Fermi level becomes unoccupied. It's pretty much the same thing which you might have inferred, but let me reiterate here for you. In metals, the Fermi energy gives us information about the velocities of the electrons which participate in the ordinary electrical conduction. The amount of energy which can be given to an electron in such conduction processes is in order of microelectron volts. Energy band gap. Take a look at the energy band gap. The band indicates whether the substance is a conductor, semiconductor, or an insulator. A very large band gap like this purely indicates that the substance is an insulator. It is because it takes a huge amount of energy for the electrons to jump from the valence band to the conduction band. Hence, there will be no conductivity. When there is no gap or a small band gap like this, then it's an indication that the substance is a conductor. Small band gap essentially allows for a constant conductivity. And lastly, when there is a small band gap like this as shown here, it just means that the conductivity in this case is somewhere between that of an insulator and a conductor. Hence, this kind of a substance is known as semiconductor. Recap. In this lesson, we learned
Right.
conductor.
Right. Now, with this, we'll just end our today's class. I hope you have understood the energy bands, right, in the solids, right? So you can just see it. If you have any doubt, you can ask me, uh, right, by chatting or by giving your queries in the doubt sessions, right? Thank you, everyone.